right, we are at this point going to talk about what we call complex solutions. And complex solutions are what happens when we solve a quadratic and we get a complex or imaginary answer. So let's talk about a couple of things. Let's start with a really easy problem. Let's start with 2x squared plus 32 is equal to 0. And let's work our way through solving this, and then we'll make a couple of points when we get to the end. First of all, if I would ask you to solve this, the first thing you would want to do would be to isolate the x squared. So we would move this 32 to the other side, and we would get 2x squared is equal to negative 32. Divide by 2, x squared is equal to negative 16. So all of that is fairly normal, and so is the next step. X is equal to, we take the square root of both sides, plus or minus, because we don't know which root we're using, the square root of negative 16. Well, here's where the problem comes in. We have the square root of a negative number. And we learned earlier in the year what we do with that. We use Euler's notation, and when we use Euler's notation, we can take the square root of that 16, it's 4, but our square root of negative 1 becomes the imaginary number I. So the solutions to this quadratic are x equals plus or minus 4i. Well, what else do we know? We also can find the discriminant for this quadratic. So we want to go back and find this discriminant and then look at another piece of what the discriminant tells us if we have a negative discriminant. So if we plug this in, b squared, so 0 squared, minus 4a, a is 2, c, which is 32, gives us our discriminant, and our discriminant in this case is equal to negative 256. So we talked about in the last video, when we talked about the discriminant, that if we got a negative discriminant, we knew there were no real solutions. Well, that's true. There are no real solutions to this quadratic. But we have now seen that when we say there's no real solutions, we know something else about our quadratic. We know that it has two complex or imaginary solutions. These two numbers, 4i and negative 4i, are complex or imaginary numbers, and they are still solutions to our quadratic, even though they are imaginary. In this case, those complex solutions do not translate into an x-intercept. They are considered to be solutions to our quadratic, but they don't make x-intercepts. So this would graph in such a way that it never crossed the x-axis. Notice also that we have two solutions. We have a plus 4i and a minus 4i. My factors here would be x minus 4i and x plus 4i if I wanted to write that in factored form. Those two solutions don't give us an x-intercept, but they also always occur in pairs. You will never see one complex solution without another complex solution. And that other complex solution is its conjugate pair. Imaginary numbers like this always have imaginary friends. You are always going to have, if you've got 4i as a solution to your quadratic, you are going to have negative 4i as a solution to your quadratic. They're never going to occur just one at a time. All right, so what if our solution, our quadratic, was just a little bit more complicated and we had to use the quadratic formula? It still works. You still have the same sort of situation. Let's take this quadratic, 2x squared minus 3x plus 5 equals 0. If we take this and we figure out what the discriminant is for this quadratic, we get b squared minus 4ac is equal to negative 3 squared. There's my b squared minus 4ac times A times C. We've simply substituted into that formula, b squared minus 4ac, to find the discriminant. And that would be equal to 9 minus 40, and 9 minus 40 is negative 31. So we know here that this is going to have no real solutions. We're not going to have any x-intercepts if we graph this quadratic. They are solutions, but they're not x-intercepts. They are complex solutions. So we know that they're going to be two complex solutions to our quadratic. So let's think about what that implies for us. Anytime I have one complex solution, I'm going to have two. I could have two complex solutions in a quadratic, or 4 or 6, or, well, not in a quadratic, in a polynomial, or I could have 4 or 6 or 8, but I'm never going to have an odd number of those quadratics, of those imaginary complex solutions in my polynomial. So let's solve this. Let's figure out what the solutions are going to be here. Let's use the quadratic formula. X is equal to negative b plus or minus the square root of, and I'm going to go ahead and fill this in even though we already know what this value is underneath the radical, negative 3 squared minus 4ac all divided by 2a. And if we figure it out as if we'd never seen it before, we end up with 3 plus or minus the square root of 9 minus 40 all over 4. And 9 minus 40 is negative 31. So 3 plus or minus the square root of negative 31 over 4. Now, I really don't care if you divide this into two fractions or you leave it as one term, but you do need to pull that imaginary I out from under your radical. We write this as 3/4 plus or minus the square root of 31, since that radical will not simplify, over 4 times I. I'm going to write that I on the outside so that this is in standard form. So these are the solutions to my quadratic. When I have complex solutions, I've got this pair, this conjugate pair of imaginary solutions.